So, how do you take an idea, something you might just sketch out on a napkin, and turn it into a powerful, organized database that can handle tons of information? Well, that's exactly what we're going to break down today. We're talking about turning a conceptual blueprint, an entity relationship diagram, into a rock-solid, functional database schema.
I mean, just think about the apps you use every single day. Your social media, your favorite shopping site. They are juggling millions, maybe even billions of pieces of data. How in the world do they keep track of every user, every post, every single item in your cart? It's not magic, I promise you. It's all about having a really smart structure.
And that structure begins with the blueprint. In our world, that's the entity relationship diagram, or ERD for short. Think of it like an architect's plan for a skyscraper. And the final building? That's our database schema. So today, we're going to be both the architect and the construction crew. Let's turn this plan into something real.
All right, first things first. Just like any good building, you have to start with a solid foundation. For us, that means creating our basic tables. This is the absolute groundwork that everything else is going to be built on top of. And luckily, it all comes down to 3 pretty simple rules. Rule 1, every main thing, or what we call an entity, gets its very own table. Rule 2, all of its characteristics, or attributes, become the columns of that table. And Rule 3, and this one is super important, the one attribute that makes each record unique, like a student ID number, becomes the table's primary key. That key is our guarantee that we can find any single piece of data in an instant.
Let's look at a quick example. Here, our student entity becomes a student table. Easy enough, right? Its attributes, roll no, name, and sex, well, those just become the columns. And because every student has a unique roll no, that becomes our primary key. You can see it's underlined in the final schema to show that it's a special one. See? It's actually pretty straightforward when you break it down.
Okay, so the foundation is poured. Now it's time to start working on the interior details. You know, data isn't always neat and simple. Sometimes you run into attributes that are a little more complex. Let's figure out how to handle those.
First up is something called a composite attribute. All this means is that it's a piece of data that's really made up of smaller parts. An address is the perfect example. You could just have one big field for address, but that's not very useful, is it? What if you wanted to find everyone who lives in a certain city? You'd have to search through a giant block of text. It's way better to break it down. And here's exactly how we do it. We take those composite attributes like name and address, and we just flatten them out. So instead of one name column, we make a first underscore name and a last underscore name column. And instead of a single address column, we have house no, street, and city. The big takeaway here is that we only want the smallest, most basic pieces of information in our final table.
All right, next up is a slightly trickier one, the multi-valued attribute. This happens when one person or thing can have more than one of the same piece of information. Just think about it. You probably have a cell phone number, right? Maybe a work number too. How do we store both of those for just one person?
So what's the solution? We can't just keep adding phone number 2, phone number 3 columns. Our table would get huge and messy fast. The really elegant solution is to create a brand new table just for that one attribute. You can see here we've made a new mobile no table. It holds the phone number itself, and it also holds the student's roll number. That roll number is the link that connects each phone number back to the correct student. It's a clean, scalable way to solve the problem.
Okay, our last special case is the derived attribute, and this one is all about working smarter, not harder. This is any piece of data that you don't actually need to store because you can figure it out from something else you already have. The classic example is age. If you know someone's date of birth, you can always calculate their age, right?
And the rule here is just pure efficiency. Don't store what you can calculate. That age attribute, you can see it with the dotted line, is completely left out of our final table. Why? Well, think about it. If we stored age, we'd have to update that column for every single person every single day. That's a nightmare. Instead, we just store the date of birth, the single source of truth, and we can calculate the age whenever we need it. It saves space and guarantees the data is always accurate.
All right, our tables are built. They're like the different rooms in our house. But a house with no doors or hallways is just a bunch of separate boxes, isn't it? We need to connect these rooms. In our database, those connections are called relationships. And the magic connector that makes this all possible is the foreign key. It's such a simple but powerful concept. You just take the primary key from one table and you copy it into a new column in another table. And just like that, you've created a direct link between them. This is what lets us pull information from all across our database. Let's start with a simple one.
a one-to-one relationship. In this example, one employee manages one department. To connect them, we just take the primary key from the employee table, which is E-code, and we add it as a new column, a foreign key, in the department table. Boom! Now we know exactly who manages that department.
Now for the most common type you'll see, a one-to-many relationship. Think of one scientist who comes up with many different inventions. The rule here is absolutely critical. You always take the primary key from the one side, in this case the scientist's SID, and you place it as a foreign key in the table on the many side, the inventions table. That way, every single invention is clearly linked back to the person who created it.
And finally, the big one, the many-to-many relationship. A student can enroll in many courses, and a single course can have many students. See the problem? We can't just put foreign keys in the existing tables. It would be total chaos. The solution is brilliant. We create a brand new table that sits in the middle, sometimes called a junction table. Here, the study table has one job and one job only: connect students to courses. It does this by holding the primary keys from both tables, the SID from the student and the C_code from the course.
We've done it. The structure is built. The rooms are all connected. Now it's time for the final walkthrough, the last inspection. These are the finishing touches that make sure our database isn't just working, but that it's also strong and trustworthy.
So this final step is all about data integrity. We run through a quick checklist. Does every single table have a primary key? Yep. Are all our foreign keys pointing to the right place? Check. Then we can add other rules called constraints. We can say a name field can not be null, which means it can't be left empty. Or we can make an email address column unique to make sure no two people have the same one. These little rules are like the security guards for our data, making sure it stays clean and reliable.
And there you have it. We've gone all the way from a conceptual sketch to a logical, powerful database structure ready for data. You've seen how to translate that blueprint into a real schema, one rule at a time. And these principles, these are the foundations of almost every single app and website you interact with. So now that you have the tools, the only real question left is, what are you going to design next?